Welcome back to another explainer. Today we are popping the hood on the modern machine translation pipeline. We're going to see what really happens when messy, unpredictable human language collides with raw code here in 2026. For 30 years, translation was the massive challenge that fundamentally funded and drove natural language processing research. And honestly, it absolutely continues to push the boundaries today. So get ready, because we are going to unpack exactly how state-of-the-art systems handle the sheer chaos of human speech.
Let's kick things off with a classic example that proves perfectly why simple one-to-one word mapping is just, well, it's completely impossible. If you take the English phrase, "I miss you," and translate it into French, you get "tu me manques." But if you translate that French phrase literally back into English, it means "you are lacking to me." The subject and the object have completely flipped. No basic word-level alignment survives that kind of structural shift. Word orders vary, sentence lengths change, and human idioms stubbornly refuse to line up neatly. It's like a giant puzzle where the pieces constantly change shape.
To understand how modern engineering actually solves this, we'll cover 5 key things today: the translation problem, the modern MT pipeline, measuring translation quality, surviving production failures, and finally, choosing the right tool. Starting right off with Section 1, the translation problem, and the inherent chaos of language.
Take a look at this quote, because it absolutely hits the nail on the head. That stubborn gap between human and machine communication, it's literally the exact catalyst that forced the invention of the architecture powering our entire AI boom today. Every major leap forward happened because translation quality was highly measurable, yet incredibly difficult to actually perfect. Without the desperate need to solve machine translation, we simply wouldn't have the large language model paradigm we rely on today.
Moving right along to Section 2, the modern MT pipeline, and what the 2026 standard actually looks like. So when you're building this out, 3 crucial operational choices are going to drive your real-world translation quality. First is your tokenizer. Modern systems rely on a shared vocabulary tokenizer, specifically sentence piece BPE, which is trained on a massive mixed language corpus. This shared vocabulary is the secret sauce enabling zero-shot translation between super rare language pairs. Second is model size. Sure, you can run Meta's 600 million parameter NLLB200 on your laptop, but scaling up to the 3.3 billion parameter version? That's the published production default for a reason. Third is your decoding strategy. You absolutely must avoid the greedy decoding trap by setting your beam search width to 4 or 5 and applying a length penalty so the model doesn't just spit out overly short, broken sentences.
But hey, we have to remember these models aren't magic, right? They require highly specific programmatic prompts to function. When you make an API call, you have to pass a parameter like srclang just to tell the tokenizer which script to expect. Then you use forced_BOS_token ID to tell the decoder exactly which language it needs to generate. And a quick heads up, these tricks are model-specific. NLLB's conventions will not work for MBART. If you mix these up, your whole pipeline breaks instantly. Total nightmare.
All right, so how do we know if it's actually working? That brings us to Section 3, measuring translation quality.
For the longest time, the default measurement was BLEU. It's a fast, reference-based score measuring word overlap. But honestly, it can be incredibly frustrating. It grades from 0 to 100, where 30 is usable and 50 is exceptional. The catch here, if you're comparing 2 models and the difference is under one single BLEU point, you are basically just looking at statistical noise. It tells you almost nothing.
Because of that noise, the 2026 gold standard is this 3-tier hierarchy. You never rely on just one metric anymore. At the base, you ship with fast heuristics like chrF, which is much better than BLEU for morphologically complex languages. Then, for high quality, you move to learned neural models like Comet, which actually compares semantic similarity. Finally, at the very top, we have LLM-as-judge. By prompting a massive LLM with a strict rubric, you can evaluate translations without any human reference text at all, and it matches human agreement like 80% of the time. That is a massive game changer for rare, long-tail languages.
Now, a super quick but absolutely vital warning about those base heuristics. Always use the sacred BLEU framework. BLEU scores can fluctuate wildly depending on how text gets tokenized before scoring. Sacred BLEU normalizes all of that, so scores across different research papers are actually comparable. Rolling your own math is exactly how misleading benchmarks happen. Just don't do it.
Which leads us into the really fun stuff. Section 4, surviving production failures.
This brilliantly illustrates the 80-20 rule of machine translation in the wild. Your modern pipeline will translate fluently and accurately about 80% of the time. You'll literally think you've solved language. But
It will silently fail in that remaining 20%. And I emphasize silently because the output will usually look perfectly readable to anyone who doesn't speak the target language, completely masking the fact that it's dead wrong. Knowing this upfront will save your team weeks of debugging.
So what are these silent failures? They generally fall into 5 main traps. First, it's hallucination. The model just flat out invents content that wasn't there. Second is off-target generation, which means accidentally translating into a completely different language, no good. Third is terminology drift. Fourth is formality mismatch. And fifth is length explosion, where super short inputs, like under 5 tokens, cause the length penalty to basically fall off a cliff, giving you massive, rambling paragraphs for a 2-word input. Let's zoom in on a couple of these.
Let's look at terminology drift. Imagine you have a simple sign-up button. If it gets translated as s'inscrire on one screen, but créer un compte on another, you've got a problem. For user interfaces, strict consistency actually matters way more than raw, poetic translation quality. You have to mitigate this using glossary-constrained decoding, which essentially forces the model to always lock in your specific brand terminology.
Another massive headache: formality mismatches. Think about languages like French with the informal tu versus the formal vous, or Japanese with its complex politeness levels. If left alone, these models will lazily pick whichever politeness levels showed up most in their training data. This can completely ruin your customer-facing content if your brand is supposed to sound highly professional, but the model defaults to casual street slang. You combat this by either injecting a prompt prefix with a formality token or fine-tuning a model exclusively on formal text.
And speaking of fine-tuning, here is your golden rule for fixing any domain-specific issue. Gathering just a few thousand high-quality, perfectly aligned examples is the absolute largest production lever you have. It will vastly outperform just throwing giant, messy datasets of scraped web text at the model. Quality over quantity is the undisputed reality of fine-tuning right now.
All right, let's wrap this all up with Section 5, choosing the right tool for your stack today.
Think of this table as your ultimate, pragmatic cheat sheet for 2026. If you need broad, any-to-any translation across 200 languages, grab Meta's NLLB. If you're building a tool that has to run directly in the user's browser, where memory is tight and latency is critical, use a tiny 50-megabyte ONNX-quantized Marian model. But if you are after maximum quality, highly idiomatic phrasing, and absolute stylistic consistency, and you don't mind paying the per-token cost, then you prompt a massive LLM like GPT-4, Claude, or Gemini.
Which actually leaves us with one final, pretty provocative question to chew on. We already know LLMs are starting to beat specialized translation models on a lot of language pairs. So as these massive models keep getting cheaper and cheaper to run, and massive context windows become the absolute norm, will these specialized, highly efficient translation models just become a thing of the past? It's a huge debate, and it's exactly what the industry is wrestling with right now. Thank you so much for hanging out with me for this explainer. Keep learning, keep experimenting, and I'll catch you in the next one.